Thank you. So yeah, welcome to this first online seminar of the new year. It's a pleasure to show you a bit of my work. I've been doing most of my PhD, which is about wind clumping. That's basically my whole PhD, but also including magnetic fields. So that's where my focus will lie today. Since it's a rather obscure topic, I will also start to introduce some concepts first before we go to the work I've been doing, so that you can actually have a better idea what's going on in the background. And for that, I will just first start with radiation or radiating fluids. So what does that mean? So radiation, that's normally something you can see from an object in space, and until a few years ago this was the only way to see something and learn something from an object in space. But I'm actually more interested in situations where radiation governs how this system behaves. So it's still providing information, but also sets how the system dynamically evolves. And that occurs in quite many places in astrophysics, on very small scales when you have star formation, to somewhat larger scales if you have stars, which most of people in our institute are studying. And even on galactic scales, when you have very active galaxies, there is also radiation. Matter interactions are quite important. So what do they do? So they, of course, shape how this system evolves. It provides a chemical feedback to the surroundings. And in some cases, or actually in most cases, it's also providing a feedback back to the object that's emitting the radiation, whether this is a star or a disk. And my focus today will be on stellar winds, since that's what our group is doing, and specifically stellar winds of massive stars. So massive stars, what is that? There's a bit definition dependent. For me, is something that either becomes a neutron star or a black hole at the end of its life. And that's typically a star that starts its life with roughly 9 times the mass of the sun or more. But if you really would ask me about a massive star, for me, there's only one in the universe. That's an O star that I always study, and that's just 50 times our the mass of the sun. It's about 20 times as big as our sun, and is approximately at 40,000 Kelvin. So anything you see today is just for that star. So you don't have to remember any other star, because in my universe, there's only one. And if you would evolve this star, it would become at the end of its life, of course, a supernova and a black hole. But that's stages I will not touch upon. Now, these massive stars have radiation-driven winds. If you talk to people in our group, or perhaps even people in our institute, they might not really understand what you're doing if you say radiation-driven wind, because it can mean there are several things. For example, are you working on continuum-driven winds, like in HEB stars, or in disks from active galaxies, or accretion disks? Then you have that. If you're doing line-driven winds, then I'm very happy to listen to you as well, because that's what I'm mainly doing. And this happens in OB stars, so what's what we will be focusing on today, but also again in several types of disks in young stellar objects. And you can actually also do both of them together at the same time. And for example, to study the winds from very massive evolved stars, so like Wolf-Rayet stars, and then you should really talk to Luca and Nicolas in our institute, in my group, who have given also seminars on this last year, to see how that actually works then. But for me, for today, it's just line driving. And line-driven winds, so there's a very nice theory for that. Like most stellar wind theories, that has been developed quite a while ago when the first observations or high-quality observations became available. And for line-driven winds, this was due to Castor, Abbott, and Klein, or CAK for short. So I will use that acronym sometimes. And it's very nice. It has a lot of similarities in basic assumptions like our solar wind model. It's steady state, it's very homogeneous, and it's nicely spherically symmetric. So if you work this out, then you can actually uh, retrieve what the impact is of the radiation onto the wind parcels. And it's a very nice analytical formula that provides you the corresponding acceleration, which basically depends on a few parameters, which are here called alpha and cuba. So that are setting how the spectral lines basically behave in the wind. And if you want to know more about that, then I suggest you watch Luca's seminar last year, that you can see all the nice atomic physics that determines these parameters. And then there's a very peculiar occurrence of that the acceleration is actually caused by the acceleration itself. And that type of wind theory has been quite successful in explaining like global properties of line-driven winds. So how does this a bit work? So how does the driving actually work? There are really two key ingredients that you need, and that's displayed here on the figure, which I will explain briefly. So first of all, you need photons, of course, that interact with an atom or an ion, but these photons can only interact over a very small range with the ion, and that's basically what's denoted in the gray shaded area here. So our star is on the left, and the farther we go to the right, the farther we go away from the star. So what happens? These photons near the star impact on material. So this material gets a kick outwards. And then there's actually the second important effect, namely the Doppler effect, which shifts the material out of the shadow, how we call it, of the underlying material. And that basically means that it can interact with new stellar photons. And then the process basically repeats itself. And this then is in some cyclic way repeats itself, and you get an acceleration. So your velocity increases with distance from the star, which is exactly what we see here. So that's the basics of line-driven winds that you need to know. Let's now look at magnetic fields in massive stars, and that's a quite peculiar thing, as I will show you quite soon, because for example, when we look at our sun, we know it's magnetic. There are all types of phenomena that are related to this magnetic field, like sunspots, flare eruptions. And it's basically because our sun has a very special type of outer layer, and also stars smaller than our or less massive than our sun, because they are either partially convective or fully convective. And this is very nice if you want to generate magnetic fields, because in order to generate a magnetic field via dynamo, you need convection and some rotation. And that's both fulfilled in these type of stars. Now, if you go and look at the interior structure of a massive star, it's actually quite the opposite. So it has a small convective core, but most of it is radiative layers. So we transport by radiation. And this cannot really generate a magnetic field. So the question is, if that's true, how can we see magnetic fields in massive stars? And this is more or less an unresolved question in our field. So you could try to make some dynamo models, but you will see they fail. So the general idea is that the field stems from some primordial origin. Now, primordial origin is also a rather broad term, so it can mean many things. So Is it captured from the star formation phase? Is it from the protostellar phase, from the accretion disk? Or like recently, it was proposed that in the protostellar phase, the merging of massive stars uh, or the merging of the radiative layers might actually generate the magnetic fields we see in our massive stars. So, but it remains a bit open. Question is still being investigated, but that's not really what I want to focus on. So I just assume that the magnetic field is there. I take that for granted. So if we go and look then at our magnetic stars, there you will see that they have some very peculiar properties as well compared to, for example, our sun or solar-like stars. Because on the contrary than our sun, the fields are quite strong, which means they have some like kilo-Gauss-like structures, sometimes even several tens kilo-Gauss. They're very organized and stable, and that means basically they're dipolar in our case. And they're also very rare. So it's a very rare thing to have massive stars that have magnetic fields. So in our galaxy, there's only 7% of them whose magnetic fields. And outside our galaxy, we don't even know. They're probably there, but we haven't detected them. If we look specifically at the plot I show you, so this is just a Hertzsprung-Russell diagram, except for magnetic massive stars now. So the gray area is the whole main sequence. So what you see is that most of them that we observe, they're all main sequence stars, or in some cases, there are Herbig stars plotted as well. So they're still coming towards the main sequence. So we haven't seen either evolved magnetic massive stars. So that's also quite rare. So there are many puzzling questions about this, which require an answer. Now, since I'm studying stellar wind, so I don't really mind where the field comes from. I take it for granted, like I said. So, and I wonder then what's the effect of the magnetic field on the wind? And there are basically two really important effects. First of all is that part of the wind will get confined or will get trapped. And I will come back to that later. This is more or less what I will be focusing on today. And you can also see this in several wavelength bands, either in the optical or the X-rays, where you can probe this confinement or this trapping of the stellar wind and learn something about the system. On the other hand, your magnetic field also provides an additional mechanism for angular momentum transport, which is very pronounced for massive stars, magnetic massive stars, because they're basically not rotating compared to non-magnetic massive stars, which rotate quite fast and with a few hundreds of kilometers per second. So that alters, of course, the evolution then of the star. So because the trapping of the stellar wind reduces its mass loss rate, and of course the angular momentum transport leads to a magnetic braking. Both effects one could study in a stellar evolution setting. But I will discuss a bit the confinement today, not really focus on mass loss rates, but mainly the confinement and some more other wind physics. So how can you see or how can you learn about the confinement of a massive star or a magnetic star in general? Then we can look again at our sun. And if you were to show me this picture, I could perfectly tell you where the solar wind is confined and where it's not. And that's roughly this egg-shaped figure. So where there's a confinement, that means that my magnetic field is much stronger than the wind. When the magnetic field is weaker than my wind, then the wind is winning and the wind is not confined, obviously. And there will always be a point in space where the wind will get stronger than the magnetic field, simply because the magnetic field decays faster than the wind with radius from the star. So one can also quantify this interaction a bit more rigorously. And we call this in our field then the so-called eta parameter. So it's basically a comparison between the energy contained in a magnetic field and the energy contained in the wind, which is the kinetic energy. So if you take this ratio, you get a quantity. Now this is in general not so useful quantity because my magnetic field, my density, my velocity, they're all complicated functions of position. But you can actually rework this then and split a constant out of it and a function of position. And this constant is what really matters. That's what we call the wind magnetic confinement parameter, or eta star. And it basically tells you for a given star whether it's magnetically confined, so when it's larger than 1, or when it's not magnetically confined, when it's smaller than 1. So it's obviously the case bigger than 1 that is of most interest. The other is more of academic interest. But I will nonetheless show it today to illustrate how it basically looks. Now we have then this confinement, so let's look at this in a bit more detail. So when our eta star is bigger than 1. So what happens? So for a massive star, there are basically 2 types of situations that occur in terms of confinement. And you get 2 types of different magnetospheres, like we call them. So on the one hand, we have something we call a dynamical magnetosphere, and the other hand, you have something we call a centrifugal magnetosphere. And both are basically governed by just 2 parameters. So for the dynamical magnetosphere, it's only something we call the Alfvén radius you should care about. And that just sets where my last closed loop is of emerging from the star. So everything within the Alfvén radius will be magnetically confined, so cannot escape. If my star is actually rotating, and rotating means quite fast, then there's another parameter, another spatial point that becomes of interest, which we call the Kepler radius. So what happens in that case? You get a centrifugal magnetosphere, and this centrifugal magnetosphere still has a dynamical magnetosphere within it. But above this Kepler radius point, what happens is that the centrifugal force is in balance with gravity, and you get some kind of accumulation of material in the equatorial plane, or some kind of disk-like structure. Now, it's not really a disk, but that's not so important for today, because I will be exclusively focused on dynamical magnetospheres. And there's a very good reason for that, because if you look at our massive magnetic stars in our galaxy, you can classify them based on these 2 parameters, so the Alfvén radius and the Kepler radius, and it gives you a very neat overview. And you can learn a lot by just looking at this diagram I show you here. Because if we go and look at our dynamical magnetospheres, for example, we see that they're all O stars there. So all O stars in our galaxy have dynamical magnetospheres. And since for me there's only an O star in the universe, I'm naturally in that part of the figure. But you will also see that they're all slowly rotating, and they have quite weak magnetic fields. They have magnetic confinement, but it's not so strong. Whereas if I go to B stars, so they have predominantly very high magnetic fields. They have very strong confinements, and they're also very fast rotating. So this diagram learns you a lot of the basic properties of the star. And not only that, so you can make similar figures for emission or absorption in certain spectroscopic bands. You will see that dynamical magnetospheres will show different emission patterns than centrifugal magnetospheres. So it's very powerful tool, just these 2 parameters, to learn something about a magnetic massive star. Now that's where the magnetic field's coming from. So let's look at the wind clumping instability. So that's what I have been paid for the past 4 years. So remember that in the beginning I talked about line-driven winds. Now, I omitted some details, some really nasty details, which we will explore a bit now. Because when this theory by Castor, Abbott, and Klein was developed, so the smooth and homogeneous winds, not so long after that, people saw in observations that these winds could not really be smooth. So something like structures must be present. So the question then is, how can one understand this? And one can do this from a mathematical point of view or a numerical point of view. But back in those days, the computers were not that great compared to what we have now. So our first analysis is based purely mathematical. Now the question is, what is an instability? What do I mean by that? And I noticed that when I talk to non-scientists, they sometimes think something completely different. So they think instabilities, bad things happening in nature, finance world is unstable. You have mentally unstable people, but that's really not what I'm doing. So I have to tell them no. So what I mean with instability is that's something when you have a cappuccino, for example, there's a very nice instability occurring. Or if you cannot cook soup, then you will also see another instability arising. If you look at the weather, you sometimes might see very interesting instabilities, and some of them also occur in astrophysics. And I'm studying one of them, and not the one I show you here, but one specific to a line-driven wind. And so how does this look from a mathematical point of view? So how can I understand this? So this can be done very simply by just looking at the equation of motion. So you neglect any irrelevant force, so except the force that's relevant, namely the line acceleration. So your equation of motion becomes quite simple in 1D then. And what I want to do now is imagine that I have a very smooth medium. What happens when I perturb this slightly? So you can make the analogy, for example, with a filled bathtub. So if you put your finger into the water, not very hard, but gently, you will see that a concentric wave will travel across the surface of the water in the bathtub. And that's basically what mathematically one can also do for any other system. So you introduce plane waves to the system. So your perturbation, you model as a plane wave with a certain amplitude, a certain wave number, and a certain wave frequency. If you do that, if you work this out, there's something we call linear analysis, because your nonlinear hydrodynamic equations become linearized. So they become algebraic equations that you can solve analytically. You can find solutions for that. You can find then an expression that relates how your wave frequency should behave. Now, this wave frequency can be really anything. This can be a real number, it can be an imaginary number. In general, it's a complex number, meaning it's real and imaginary together. And in our case, so when is there an instability? That's when our imaginary part of the wave frequency is bigger than zero. Because what happens, if you look at our exponential term here, you will see that it will be positive exponent. You get e to the something positive times t. So that means that in time, that wave is growing, or that's the synonym for an unstable wave or an instability. So determining then for a line-driven wind what condition has to be satisfied, that means that the perturbation on the line acceleration scales with the perturbation in velocity. Now, determining that proportionality factor is something that's not very simple, so we're not going to do that, but that proportionality factor is the growth rate of the instability. So it basically tells you how fast the instability is growing. And for a line-driven wind, that's quite fast, so it's 50 seconds. Compared to other instabilities in nature, that's extremely fast. And I show on the figure on the right a bit how you can visually imagine what's going on. So you put a perturbation on your smooth wind, which I show in black line, the black solid line. So you include a perturbation that's initially small, but then grows very rapidly. And of course, in this case, I should almost draw a delta function, but that doesn't really make sense for the illustration. So this instability arising in our line-driven winds, so we call that the line deshadowing instability, or LDI. It's a really nasty name for a nasty piece of physics, but you can learn how this basically operates by looking at the same mechanism that a line-driven wind is accelerated, because if we go and look at a positive velocity perturbation, for example, what happens? So that perturbation goes farther away from the star. It will be Doppler shifted again, so it can start to interact with new photons. So actually its optical depth will decrease. It will get more flux and it will get more acceleration. You can also have the opposite case. If you have a negative fluctuation, so you get towards the star, you will see more optical depth, so you will actually be in the shadow of underlying material. You will receive less flux and you will receive less acceleration. So what basically happens then in your medium, you have on the one hand material that's flowing, that's going faster, faster, faster. On the other hand, you have material that's going slower and slower and slower. So your material is getting teared apart. And what happens in nature is that a shock occurs and a shock wave happens along with that. Now that is not something we can study anymore with mathematics, with linear analysis. For that, you really need a computer to do the nonlinear evolution in nonlinear analysis. And we can do this nowadays. And if you do that, what you typically find is what I show you in the figure here. So there's for my O star, the velocity and density structures in the wind after sufficient time of evolution. And what you see is a distinct two-component medium. So on the one hand, you have very dense structures, which we call clumps, and those are embedded in a very diluted medium, so which is sometimes called the interclump medium or the rarefied medium, depending on to whom you're talking. Now, why would you care about this in the first place? So it's obviously nice to see for me, but it can have important effects on observational diagnostics. So if you're doing spectral line modeling, I will briefly come back to that. And next week, there will be much more on that actually. So that was 1D. How does this look in 2D? I have two small movies to illustrate to you how this looks in 2D. So on the left, you have a global simulation. So this is a density evolution. On the right, you have a local simulation. So that's near the star. So you can really see the amount of detail. And basically, my clumps in 1D, they're basically shells. In 2D, they're really clumps. So they're small spatial structures. So they're typically, their size is like 1% of the stellar radius. So they're quite small. Now, coming back to why would you care about this? So that's for the observational diagnostics, specifically spectral lines that are so-called density square dependent. They are prone to this wind clumping. So these are recombination lines, for example. For H alpha is a very well-known example of that. But what happens if you trying to predict mass loss rates from your observations, you will actually overestimate them by a certain factor if you don't include this effect from the clumps. And of course, if you don't know your mass loss rate, you also don't know your stellar evolution, because for massive star, it's very sensitive to the mass loss rate. Now, how can one constrain this clumping? That's unfortunately not so easy. So you can do this from observations, and Callum and Olivier can tell you all about that. And actually recommend that you watch next week Callum's seminar, because that will go in a very much detail about the observational constraints on wind clumping. which I will not discuss today. And one can do this from theory, which I will discuss today. There's a trade-off, of course, that one has to do very complicated simulations that are very nonlinear. So it's also not so easy, but if one can do it, it's basically a free result from my simulation. So I don't have to do anything for that. So to give you an impression how this clumping looks inside the wind, I have a 1D simple model. So on the left, you see a numerical simulation. On the right, you see actually an observation. So it's the black line on the right. That's the observational constraint. And you see they're basically doing the same. They're showing the same trend where you have a rise in the inner wind up to about 2 stellar radii, and then it gradually decreases outwards. Of course, my simulation only extends to 10 stellar radii. This observation can go much farther, but in my simulation, that's just not doable in terms of computation time. But the overall trend is the same, which is quite nice. Now, what happens if you throw all of these things together? Then it becomes a lot of frustration and a mess, but in the end, it starts to work. And that's what I want to discuss. So I will first introduce my friends to you. So that's the type of equations I'm normally using. So if you're modeling a magnetic fluid, you're doing magnetohydrodynamics. So that means that your Euler equations are complemented with the effects for the magnetic field. So we have first our continuity equation, which remains the same, but our momentum equation is modified for the Lorentz force. We have an equation that couples the magnetic field to my velocity field, which is the induction equation. And then we have the monopole constraint, which is actually the most hardest equation to solve on a computer. Normally, you can also add an energy equation then, but I don't do that. So I remain isothermal, which means you have a very simple relation between the pressure and the density, and the proportionality factor is then the isothermal speed of sound. Now we want to describe our interaction with the wind from the lines. So we add source terms to our momentum equation, and there are only two we really need. So first of all, we have, of course, stellar gravity, which is actually modified. So because it turns out that the continuum radiation lowers the gravity a bit into something we call effective gravity. And then we have the most important one, of course, our acceleration from the lines, which is actually a very nasty expression that doesn't fit on the slides, so I'm not showing it. But if you have seen, for example, Nicolas' seminars, you will notice that except for the magnetic field, it's slightly different. So he's solving a different type of equation to describe his radiation matter interaction. So there are several ways one can do this, depending on the physical conditions one has. So what happens when you do that, when you put this in a computer and wait for a while? So let's look at our weakly confined wind. So my eta star is smaller than 1. So there's no wind confinement. So the wind will flow just outward. And what happens? I show on the left a model without instability, on the right a model with instability, so with clumps. So what do we see here? So this is after long enough simulation time, my density structure. So I see that my field lines are basically ripped open because my wind is winning everywhere around the star. So my field lines get stretched open and they basically look like a split monopole. Now, of course, if I include my instability, I have some clumps and you can still see them. They're somewhat more connected here, but on average, they're still spatially separated objects. Now it becomes really interesting if you start to look at a confined wind, and that means something like eta star bigger than 1, like 15 here. What happens then? You get actually, there are two type of interesting phenomena occurring. So you have part of the wind that's confined. So this happens in the equatorial plane of the star. So what do you see here? So basically material from the star is channeled along the magnetic field lines. It will collide in the equatorial plane, which will lead to some mass leakage, but most of the material will fall back on the star. So that's both the case for a model without instability as a model with instability. Now, the interesting fact, of course, is the model that has the instability included. My instability transforms, so it's not really spatially separate anymore. So you get these elongated features in the polar directions, or pancakes, as we call them, as we started to call them. And that's quite different from what I have seen in my model that has only a modest magnetic field and no confinement. So the question now is, if I look at magnetic massive stars, can I actually see an effect of these sheets or these pancakes in my magnetic wind on the diagnostics in a certain spectral line? Before I want to address that, I will show you very clear the distinction between a model with instability and no magnetic field, and a model with the instability and the magnetic field, a strong magnetic field, so that it's confined. So then you can really see the difference in structures. So we have on the one hand very spatially disconnected structures that propagate outward, but on the other hand you have these pancakes that are span sometimes quite huge lateral extent, sometimes even half a hemisphere of the star. So looking at diagnostics then, a prime diagnostic for massive stars are UV lines, and they have a very particular shape, some of them, which we call a PCigne line. That's shown on the right bottom figure. So on the left bottom, I show you the corresponding wind where this profile is computed from. So how does this line basically form? So you look at your star, so you will see part of it in absorption, of course. That will create everything that's coming towards you is an absorption in your line of sight. But of course, the star is also emitting in the other directions, both away from you and coming towards you. So if you add those two together, you will get this distinct shape that's you see actually very often in massive star spectra as a distinct feature. So this black line I show now here, that's going to serve as the reference line and to make my point later. So what happens if I look at the same wind, but now with an instability included? So that's the green line in my synthetic profile. So you will see that it's basically in shape almost the same. And both models are the same. The average mass loss rates of both models are the same. So any difference you see in the line profile, actually in its strength, are solely due to the effect of the clumps that are present in the wind. You'll see there, so the profile is somewhat more noisy because the clumps are distributed a bit random in space, and the absorption is also a bit less at the blue edge. Now it becomes really interesting if you start to look at a magnetic star, because then it becomes much different. And again, so for a strongly confined star, you have to look at two cases. So either the case where you look along the field, along the magnetic field pole, and the case where you look in the magnetic equator, which I will discuss later. So let's just first look at along the magnetic pole. So what happens between a model without instability and a model with instability? So not very much in terms of overall things that are not the same. So they look quite the same. But if you look at the poles, there the wind is the fastest, so the field lines get still stretched in the most radial configuration. So that means you will see the fastest material and also the most diluted material. So in the blue edge of your line profile, so at the left, you will see actually a significant reduction in the absorption strength compared to a smooth wind. Now, if you look at the equator, the situation is reversed. So what do you see then? You will actually see most of the low velocity, very high density material. So if you look then at your line profiles, you'll see that your absorption is strongest at very low velocities because there's the highest density. And again, if look between a model of no instability and an instability, you see that the overall shape is again basically the same, except that the instability model is somewhat more noisy. So there are basically two important conclusions one can draw from that. So first of all, the fact that adding an instability to your simulation in a magnetic setting does not really fundamentally change the line profile compared to a wind model that does not have an instability in it. So from that alone, it's quite hard to say something like, has the instability really an important effect on the overall shape, the overall information that's contained within the profile? But what's really important, and that's something that has been done a lot in the past, is that people were using smooth wind models, non-magnetic wind models, to model a magnetic star. So that's the black line. So my initial black line I showed. If you compare that to the magnetic profiles in the second and third panel, you will actually see that it's completely off from anything describing it. So that's a very important thing. And actually, I'm very glad that nowadays, so since 1-2 years, people actually started to discard these smooth non-magnetic wind models in their modeling of magnetic massive stars, because you're really, the parameters you're inferring from it are plain wrong. So then that brings me to the summary of my work, what I've been doing and what I've been showing you. So there are a few important things I've discussed. So if you study unstable winds, so these clumpy winds, so what happens if you introduce a strong enough magnetic fields such that you have a magnetic confinement, you will actually change the morphology of your clumps. So they become not clumps anymore, they become pancakes. Does this have an effect now on the line profiles, for example, UV line profiles, as is hard to say at the moment, because qualitatively they both look the same, whether you have a model with clumps or a model without clumps in a for a magnetic star. And of course, like I just showed you, don't ever use non-magnetic smooth winds because you don't capture all the details. You're inferring wrong parameters. So what can one do in the future then? So since this was the first pilot study, of course, the fact that the UV lines seem to be not really prone to the effect of the wind clumps doesn't mean one cannot see them. This is something we are actually somewhat doing in our group now, looking at how features like clumps in all our simulations, can we see them propagate through the line profile? And that's quite interesting, of course, because it can learn you something of the wind. Of course, on the other hand, these clumps or these pancakes, they're shocks. They're basically the result from a shock. So if you have a shock, that means material gets heated up a lot. And there's X-ray emission associated with that. And one can model, for example, this X-ray emission, which would be really soft X-ray emission in this case, and see whether this matches what we see from observations in the X-ray domain then. And of course, that's a limitation in the current models. We have our pancakes in a 2D, but what happens if we include more radiation physics, which I haven't done now, because one has to start, of course, with the most simple yet most realistic still type of model. So these are only a few things one can do, but as Joris said, so my PhD is almost over, so someone else has to take that up at some point. So having said that, that's all I wanted to say to you. And of course, if there are any questions, I'm happy to take them. Thank you.
Thank you very much, Florian. Okay, so if there are questions, please say so in the chat, and I will call out your name, trying to give precedence to, or to give priority to the younger people. Everything was clearly explained.
Yeah, it seems so. That's surprising.
Okay, once in a while it happens.
Yeah, that's really good.
Okay, so if there are no questions at all, then I think we
Perhaps we
can.
should give an exam then on Monday about this.
Maybe Janis has one.
Yeah, it's a very basic one, but thanks for your presentation. It was very interesting and very clear as well. So kudos for that. I was just wondering, so I mean, obviously you modeled, let's say the clumping behavior and all that for a specific strength of magnetic field. What would be the process, like when we observe a star, how can we tell how strong its magnetic field is, and can we, I don't know, with spectral polarimetry, is that something we can do in order to use that as an input into the model, or do we actually keep the strength of the magnetic field as a free parameter in the models? I'm just wondering, yeah, how the process would work.
Yeah. So there are two ways actually to do this. So you, like you suggested, one can derive a magnetic field from spectral polarimetry. So that means you're looking at the Zeeman effect, which has specific effects on your atomic structure, and you can measure the polarization signal from that and reconstruct the magnetic field. On the other hand, if you don't have that, so we can use models where the magnetic field is then as an input parameter, along with others, where we try to find, so we model our spectral lines or a specific spectral line, and we're trying to minimize the error between our fit and the spectral line. And from that, you will then get a best fit magnetic field structure, and along with some other parameters. But spectral polarimetry is mainly the way to do it, the way to go.
You mentioned that in your universe there's only one O-type star with a 50 solar mass, property, let's say. Would it make any sense? I know for a lot of other groups they tend to make these like huge grids of let's say models in order to already have some kind of database that you can just take your model whatever and then fit it and see how well it does. Is that maybe a plan for you before, you know, now that you have your formalism, even if you said it doesn't include everything? Is there still some plan like that?
I wish I could do that, but since a simulation takes 3 months to run.
Really? That should have been a question I should have asked before this. Yeah. Okay.
On 100 cores on a supercomputer.
Wow.
That's unfortunately not possible. So so if in terms of the instability, like making a large grid, this is quite hard, if not impossible. But you can, of course, make a better grid for models without the instability, and you can still learn a lot from the global about the global dynamics the star has, any star you would like to model then. So that is more feasible. That's about 1 or 2 weeks of computation time. So.
Okay. All right. Well, thank you so much, Florian.
Yep.
Okay, thank you, Janis. Also, Connie has a question.
Oh, I've put it in the chat, but I'll read it again.
Okay.
Thanks, Florian. I had the question that, you know, people in your community always tend to work with spectroscopy, mainly UV spectroscopy. So my question was, can you apply your theory and your simulations to make predictions on how that would be observed with micromagnitude photometry that we have nowadays for tens of thousands of stars, and you're not using any of that? Does that mean you can't get any signature of your wind predictions there, or how should I interpret this?
That's a good question, actually. So for non-magnetic stars, one can actually do that. So we can make predictions for photometry with TESS to see if we can actually see the signature of the instability in the photometric variability. Now here is, I think, the added complexity that we have this magnetic field. And the question is how especially the magnetic field behaves near the star. So is it suppressing the instability? And so you will not see any or much variability. And also how is it suppressing other motions in that region? Because it could also be that the instability signature in such a magnetic star will then be just overruled by other signatures from the like a turbulent atmosphere or perhaps even pulsations that are more prominent in the photometric data. So for magnetic massive stars, this is something we can look at. One can try to investigate. There's actually a large collaboration for photometry of magnetic massive stars with TESS. So that's certainly something one can do.
So there are no results yet on that front. Is that a good summary?
Yes, that's the summary of my long answer. Yes.
Okay. Thank you, Florian.
Thank you, Connie. Are there any other questions? If not, then I would like to thank Florian again. Thank you very much for your seminar.
Yeah, it was a pleasure.
And then I'd like to invite everyone for next week's seminar, a similar topic. Okay, thank you very much, and see you next week.
Thanks, Florian.